Said the man who feel him a fool, or he be the wise man. For the man who don't think he's a fool, he control his destiny, but he's too good for himself. For himself, for himself. Oh, I need.
Let's go ahead and look at atomic radius. Okay, atomic radius is the size of the atom. Okay, the size of the atom is defined as half the distance between adjacent nuclei. So half the distance between the nuclei of identical atoms that are bonded together. Okay, the trend decreases from left to right across a period. So you're within a period or a row, your atoms get smaller. They get smaller. Okay, within a group, they increase going down a group, so they get larger as you're going down. Okay, the reason they do these things is within the group, you are adding energy levels, so the atoms are getting more and more thicker, more and more fatter. Okay, you can think of this way. In the wintertime, you get dressed, you put a t-shirt on, you put a shirt, you put a sweater, you put a jacket, you're adding layers or energy levels, and you're getting thicker or more fatter. Okay, and then what happens when you're going left to right, what happens is you're not actually adding energy levels, so you're adding protons and neutrons. So what happens is electrons are attracted to the protons. Okay, they're being pulled in, held on by the attraction between the positive protons and the negative electrons. So as we go everything left to right, everything gets pulled in tighter and tighter as we add more protons and more electrons. Okay, so that's why they do what they do. Now the shielding effect, basically, the shielding effect is an effect where as you add these additional energy levels, all right, so the shielding effect is basically what it says, shielding effect. And what essentially happens is, let's backtrack here. One way to memorize atomic radius is we call it the snowman effect. So here's a picture of atomic radius, and as you can see, the atoms are getting fatter, going down a family, larger radius, and getting smaller going left to right. Okay, this is just showing the A group or the representative elements. Okay, transition metals do some of this stuff. This is our snowman effect, and again, as you notice, as we go down, we're adding energy levels, so our atoms are getting fatter, and as we go across, we're getting smaller. Okay, so what happens is in the shielding effect is we have these protons in the center here, all right, and then we have these electrons out here. Okay, and I'm just going to draw some electrons, and here's our one valence electrons. Let's say this is any one of these alkali metals. Here's that one electron. So there's an attraction here between the positive protons and the negative electrons, right? That's why these guys don't go flying off, is they're attracted to those protons. Okay. As we move left to right, we're adding more and more protons and more electrons, so the attraction is kind of pulling everything in tighter. Okay, but what happens is the shielding effect is the more energy levels you have, this attraction gets a little bit weaker because it's shielded, right? There's more things in the way. You can kind of think of this as two magnets, a positive end and a negative end of a magnet, okay? If there's nothing in between them, they're going to be attracted to each other, okay? If there's a little piece of paper in between them, they're probably still going to be attracted to each other. If there's a big board, a 2x4, okay, or a whole ream of paper, the attraction is weakened because of the forces are getting shielded. So that's what the shielding effect does. Shielding effect only has an effect within the groups or the families going vertical. Okay. has no effect left to right, because, again, shielding effect is dealing with addition of these energy levels, and going left to right in a period, we're not adding additional energy levels. We're just adding protons and electrons. Okay, so shielding effect only goes left to right. I'm sorry, only goes down the families. No effect left to right. No effect left to right. Okay, within this we have ionic radius. Well, that's just the size of the ion. Remember, there's cations, and these are usually smaller because there's more protons to pull and there's less electrons. Cations, we've lost electrons, so therefore we have more protons, less electrons, and the protons pull everything in tighter. Anions are larger because the atoms have more electrons. Okay, and this increases that electrostatic repulsion between the atoms' outer electrons, and this forces them apart. So we have more electrons than protons. The pulling everything in tighter is not as much, and our electrons are the same charge, so they are kind of forcing each other to spread out from each other. So here's the diagram. So here's our sodium, and then here's our sodium ion. Note the electron configuration. We lose this one electron, so now the electron configuration is just the noble gas neon, and we get smaller. Here's the chlorine atom. Chlorine atom, here is the electron configuration. We're going to gain one because we have 7, so we're going to gain 1. So now we have 3p6, and that is an electron configuration of argon, and it gets bigger. Okay, so this is an anion. Okay, and this is a cation. Cations get smaller, anions get larger. Okay, and these values, on specific values, you will never be asked about a specific value. You will just be that information will be given to you. Again, we're looking for trends. What are the trends going down? Okay, what are the trends going down, and what are the trends going across the family? Okay, so we notice here they get smaller, 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 and then they get large and smaller, smaller again. Okay, and again, the higher the cation number, the more positive charge, it gets smaller, and the more negative charge, it gets smaller. Okay, so all these are going to be your largest within the family. So again, these are the trends here within a period and within a group. All right, look at ionization energy. This is the energy needed to create an ion, or the energy needed to remove the electron. Okay, remember, ionization is either making ions is either adding electrons or taking away electrons. Now again, to take away an electron, you have to disrupt that attraction between the positive protons and the negative electrons. So you have to pull the electrons. You have to pull them apart. Well, that takes energy. To rip off the electrons from the atom away from those positive protons, that takes energy. This energy is called ionization energy. The first ionization energy is the energy needed to remove the first electron. The second ionization is the energy to remove the second electron. Okay, and on and on and on. It takes more energy to remove the second because the attraction is greater due to more protons than electrons. So, okay, the trends, we increase left to right within a family, and within a group, we generally decrease. Okay, and this is looking at a graph of the first ionization energy. So the trend is, within a family, it increases left to right, increases. There's a family, there's a family. I'm sorry, there's a period, there's a period, there's a period, there's a period. And then within the groups, or the families, there's all your noble gases, and what it actually decreases. Okay? This diagram right here, I believe, does show up on the periodic table. So again, always look on any graph, just look at your axis, make sure you understand what's going on with the axis, and then look at your data. Okay? Now we're going to review on the octet rule. This is atom tends to gain, lose, or share electrons in order to get a full 8 valence electrons. That's the octet rule. So that's kind of why we look at why ionization energy happens. Why would we remove electrons to fulfill that octet rule? Okay. This is looking at electron configuration of sodium atom. There's the 1 valence electron. Now it's gone. Okay. This is a sodium ion, and if you look at this, 1s2, 2s2, 2p6, this is the same as neon. Now, I'm not saying that the sodium has turned into a neon. I'm saying that they had the same number of electrons for the same electron configuration. Since it lost an electron, we form a positive cation. This is looking at the energies, and look what happens for lithium. Okay, lithium normally has 2 valence electrons. To remove the first valence electron, 520 kilojoules per mole, and to remove the second one, 7,300, a huge increase. And again, that's because you're not taking away the protons, so the protons are having more pull on those less electrons. As you take away the electrons, it gets harder to do that because of the attraction between the protons. Okay, the last thing I want to look at is electronegativity, and this one you kind of really need to know. This is a huge one. We'll look at this later. This is the ability of atoms to attract electrons in a bond. All you really need to know is this is the most electronegative. This is the least electronegative. So F is the most. This is the least. We decrease going down a family. We increase going across. Noble gases they don't bond. There's no chemical bonding. They don't bond, so there's no electronegative value. So fluorine is the most, francium is the least. The trend is pretty much decreases moving down a group, increases going left to right. These are looking at trends again, and this is basically, to break it down in 30 seconds, is when you have a question about this, all you do is you look at your atomic radius, you draw your snowman. Just draw your snowman. Okay? Increases going down, decreases going left to right. That's the only one that follows that trend. Okay? Increases, decreases. The others do the opposite. If this guy is increasing, getting fatter, the other ones are decreasing. If we're getting smaller going left to right, the other two are doing the opposite. They do the opposite. Shielding effect, which is not on here, the shielding effect going down increases. No effect going left to right. Shielding effect has no effect going left to right within periods. All right, you should do those reflection questions here. Make sure you know this information, and that should do it for the lax flexor, and then we'll have a quiz or test coming up. Look at the calendar for that date.